Good morning, discrete mathematics students. This is Dr. Sweeney. Today we're going to be looking at conditionals, and conditionals are an incredibly important aspect of logic and especially mathematics and science. In fact, we can't have mathematics, we really can't have science, we can't have computer science or anything else that's built off of it without conditional logic. And one of the challenges of conditional logic is that oftentimes students will confuse the truth of the propositions that make up a conditional with the entire truth of the conditional. And so one of the things that I'm hoping to do here is I'm hoping to clarify that, make it easier to understand why it is that we have the truth table for the conditionals so that you can actually understand mathematics a bit better. So what is a conditional? So a conditional is a compound proposition that posits a relationship between two or more what we call atomic propositions. So these are smaller propositions that then go in to make up the larger conditional. We write it as P, and we say P implies Q. And we're going to see that a lot, but when we're just talking about the logic, we say P implies Q. There are two parts to the conditional. On the one hand, we have the P part, the part in the front, and that's called the hypothesis. Then we have the sign, this arrow, which means like an implication. And then we have Q, which is called the conclusion. P is not always the hypothesis, and Q is not always the conclusion. It actually has to do with the position in the conditional. So you really want to make sure that you understand that, because oftentimes you're going to have different atomic propositions that'll be in the conditional place, and you'll have different atomic propositions inside of the conclusion place. So remember, it's not what makes the hypothesis is not that it's P, and it's not the conclusion just because it's Q, it's the location within the implication. So let's look at some other ways to express P implies Q or our conditional in English. On the one hand, we have P implies Q here, which is what we've been talking about from a logical perspective. That's the one that gets used most for logic, but you will see it sometimes stated inside of English. P only if Q. Notice in this case that the Q, the conclusion, comes after the if. But notice before the if, we have an only. And that actually changes the meaning of the sentence, allowing for our hypothesis to come first and our conclusion to come second. P is sufficient for Q, and Q is necessary for P are both ones that you'll see quite frequently inside of mathematics and also inside of science. One of the things that I do whenever I'm working with conditionals and I want to change conditionals from English into logic is I'll go through it and I'll have this list. And this list actually allows me to kind of look at a sentence and say, okay, well, which one's the hypothesis? Which one's the conclusion? Then I go in, like I did before, I'll state which are my atomic propositions, and then I can just write out P implies Q. That allows me to then go through and work inside of logic. It allows me to do truth tables. It allows me to do logic proofs as well. And it makes things a lot easier. So kind of keeping something like this next to you until you become a master at working with conditionals could be really handy. Now comes to the somewhat difficult proposition, part of the pun, of figuring out whether or not a conditional is true. And this is actually where a lot of people get really confused because it's kind of tricky to think about the entirety of the conditional separate from the truth of its propositions. So what we're trying to do is we're trying to determine if this entire statement, this entire relationship between two atomic propositions, P and Q, is in fact true. And so what we're going to do is we're going to use a very specific rule, and it is this. When the hypothesis is true, the conclusion must be true. Or, and this is an exclusive or, so these two things cannot be true at the same time, the conditional proposition is false. So what we get here is that when the hypothesis is true, the conclusion must be true. And so what that means is that if I have P equals true, and I know that P implies Q is true, that means Q must be true. In all other cases, for example, when P is false, we're actually going to have that the conditional is going to remain true. That's a little bit tricky, but all we want to do is we just want to think about for right now, if I know that my hypothesis is true, and I know that the conclusion is true, that's going to give me that Q is going to end up being true. So let's take a look at this in English and hopefully to help you make sense of why that's the case. So let's say, for example, I have this. If the radius of the circle is 3, then the diameter of the circle is 6. So I'm going to say that r equals 3. That's the radius of the circle. I know that the diameter is 2 times r. So d equals 2 times 3, which is 6. Now, if you think about this, you want to think, okay, well, that's true. If I know that the radius equals 3, then that means that forces the diameter to equal 6. Absolutely true every time. And so hence the conditional is true. Now, let's see what happens if, say, for example, we have the radius. So let's say r equals 4. So if r equals 4, the proposition P, in this case, or the hypothesis is false. That's what happens if r equals 4. In this case, it doesn't matter whether or not the conclusion is true or false or not. So the diameter, d, is going to equal 2 times 4. Okay, so d equals 8. Now, the thing is, these two, they have no effect on the conditionals. No effect at all. The reason why is because the conditional really doesn't make any statements about what happens if r equals 4. It is really only about what happens when the radius of the circle is 3. When the radius of the circle is 3, the diameter has to be equal to 6. Now, in addition to that, we could, in some weird world, although this is not the case, we could have the diameter of the circle actually be equal to 6. Great. Okay? And the radius of the circle not equal to 3 for whatever reason. Again, maybe it's a strange world. We've got, some kind of strange way of measuring things. In that case, the conditional is still true. Okay? So, as long as this is true, that is that the radius equals 3 and the diameter equals then 6, that means the conditional is true. Let's take a look at another example, hopefully to help make more sense of this. Let's say, for example, that I have, let's say if x squared is positive, then x is positive. We could have, say, for example, we say that x squared equals 1, and then x equals 1. So in this case, x squared equals 1, the p, or my hypothesis, is true, and the conclusion here is also true. So in this case, in this particular instantiation, what we have is that we have the hypothesis is true, the conclusion is true. But we have a problem. We know we could have x squared equal to 1, hypothesis then equals true, but then you can think of the other option, which is that x equals negative 1, conclusion equals false. We have a special name for this. This is actually called a counterexample. And the counterexample, this shows the conditional is false. So in this case, when we have an instance, just one instance, in which the hypothesis is true and the conclusion ends up being false, this ends up meaning that the entire conditional is false. Sometimes it might be true, but under all conditions it is not, and so consequently we have to say that the conditional is in fact false. And that's why we actually have the setup that we have. Now, again, if it's the case that we have x squared is negative, it doesn't really matter because the statement's not about what happens when x squared is negative, or when x squared equals 0, for example. Well, if x squared is equal to 0, x squared is not positive, x squared is in fact 0, which is neither positive nor negative, and x is also not positive or negative, it's simply 0. But in this case, that's not what the conditional is about. The conditional is about what happens when x squared is positive. And so, since it's the case that I can't count on x being positive as well, the conditional is false. So P implies Q equals false. And that's how we actually end up with the truth table that we're going to end up with. Early on, when I'm really working on this, until I can kind of really get a good understanding of why it is that our conditionals work this way, the truth table might actually be really handy for you to work with. From this basic idea, we're going to derive our truth table for conditional statements. That is, that we're going to have, when P is true and Q is true, we'll have P implies Q is true. When P is true and Q is false, though, that means that we're going to get P implies Q is false. So anytime this occurs, we end up with the conditional is actually false. If P is false and Q is true, then P implies Q is going to be true again. Because again, we only really care what happens when P is true. When P is true, Q must be true. Otherwise, P can be false, and we still have the conditional be true, and that's going to be the case with both of these examples. We now have three different kinds of propositional statements that are built off of our original conditional. We have the converse, the inverse, and the contrapositive. In this case, we are going to imagine that we have P implies Q, where P starts out as our hypothesis and Q starts out as our conclusion. These three different kinds, what we're going to do is we're going to manipulate P and Q, where our propositions are, and whether or not they're negated, and that'll actually develop our converse, our inverse, and our contrapositive. The converse, it makes the hypothesis the conclusion and the conclusion the hypothesis. We'll call this a switch. So essentially, we're going to switch our atomic propositions, their position inside of the conditional. So we're going to get Q implies P, or if Q, then P. And again, what you'll notice is that what we've done is we've just changed the position of the propositional. So you'll notice, though, too, that our truth table's changed, because now Q is in the hypothesis position and P is in the conclusion position. So when Q is false and P is true, we still have Q implies P to be true. It's when Q is true and P is false that Q implies P is false. And that's because now the hypothesis is true, but the conclusion is false. And in a conditional, whenever that relationship happens, we have a false statement. Next, we have the inverse. What happens with the inverse is we're going to negate the hypothesis and negate the conclusion. So we'll negate P, we'll negate Q, but we'll keep them in the same place. So not P implies not Q, or if not P, then not Q, right? And we'll utilize our negation symbols. Notice now my truth table, when we have P is true, not P ends up being false, not Q ends up being false, and so we get not P implies not Q. We're only going to be looking at these two sections, these two ones, the not P and the not Q. So we have false implies false, that's true. If we have not P is false, not Q is true, that's still going to be true because our hypothesis is false. Now, in this third line, what we get is not P, the hypothesis is true, but not Q, the conclusion is false, and so hence our implication is false, okay? And in the last case, we have the hypothesis is true, the conclusion is true, so we get true. One key thing that we're going to talk about when we talk about logical equivalence is we're going to notice that both the converse and the inverse, they end up having what we say the same truth table. That is no matter what P and Q are, we end up with the conditional actually being, or the converse and the inverse having the same truth. TTFT, as we say. The last one is called contrapositive. What we're going to do here is we're going to switch and negate the hypothesis and the conclusion. So this is not Q implies not P, or if not Q, then not P. And what you'll notice inside of your truth table is now what we get is we get a truth table that's going to end up looking identical to the truth table for our original conditional. So I'll actually write that out. If you remember, P implies Q. What we get is we get T, F, T, T. That is that our hypothesis is true, our conclusion is false. And in this case, not Q is the hypothesis, and the conclusion is not P, so true implies false, and that's why we end up with the false. So what you want to notice, there's a couple things that you want to get here. One is, what is the converse? What is the inverse? Right? How do we get them? And then this contrapositive, and this is really going to be hugely important for when we do proof, is the contrapositive is equivalent to the original statement, the original conditional. And we're going to utilize that when we actually go through and do proof. The last thing we're going to look at is something called the biconditional. And the biconditional is a proposition where both the conditional and its converse are true. This is super powerful in mathematics. Essentially, when we have a biconditional statement be true, this means that the two atomic propositions, P and Q, are equivalent. And in algebra, they'll end up being equal. We can say we can replace one with the other. You'll see these things like trig with like trig identities. Any kind of identity is in fact a biconditional. Any definition is in fact a biconditional. If I have this true, then this other thing must be true all the time. And if I have this other thing be true, then the first thing is true all the time too. And what we'll do is we'll actually annotate that with this double arrow. P, if and only if Q is what we say. So P is necessary and sufficient for Q. What you want to get is you can see some of these examples. Like A is a triangle if and only if A is closed and has only 3 sides. If I know that A is closed and has only 3 sides, then I know that A is a triangle. If I know that A is a triangle, then I know that A is closed and has only 3 sides. I know them both to be true all the time for each other. That's not necessarily true with the conditional. Remember that we can have the conclusion be true and the hypothesis be false in some cases. But in a biconditional, that never happens. We always have to have, if the hypothesis is true, the conclusion is true. It'll also mean for us, and we'll see this in the truth table in just a second, that if the hypothesis is false, the conclusion must also be false. So let's see another example. X plus 8 equals 15 if and only if x equals 7. So if I know that x plus 8 equals 15, then I also know that x equals 7. This is always true. And you're like, oh, okay, well, that makes sense. If I substitute 7 in for x, I get 7 plus 8 equals 15. Great. If I subtract 8 from both sides, I get x equals 7. So you can see that these two statements, they in fact are equivalent statements. They are true. For one to be true, the other one has to be true. And pretty much all of algebra is going to be built off of conditionals. So let's take a look at the truth table. What P implies Q is going to be, it's equivalent to, or it's the same as P implies Q and Q implies P. So essentially, when we have these two be true, throw them into parentheses if we need to, then we know that we have P if and only if Q. So let's actually construct the truth table for this. So true, true, we know that both the conditional and its converse are going to be true. True implies false. We have this true, and that's going to be false. Excuse me, backwards. This is false. The converse ends up being true. Because Q is now false. False implies true. That's true. Other way around, P implies Q. False implies true. That's true. False, true implies false, though this is going to be false. And then false implies false. Remember, P implies Q is going to be true, and Q implies P is going to be true. So now what we want to do is we want to say, well, we've now got this and statement, which means, if you remember from our compound propositions, we know that and is only true when both statements are in fact true. Okay? So we look, we've got our conditional and its converse. This first line, both are true, true, true. But the second line has one of them be false, so that's false, false, and then finally true. So what you'll see is that when P is true and Q is true, the biconditional is true, and when Q is true, P is false, and Q is false, we also have to have the biconditional to be true. The value of this is to know that in a biconditional, if P is true, then Q must be true, and vice versa. But it also means that if Q is true, then, if Q is false, then P is false, and vice versa. From a logical perspective and from a mathematical perspective, this means that P and Q are equivalent. And this is a very powerful thing to have happen, because once it happens, it essentially means that anytime where I see P, I can substitute Q. And anywhere I see Q, I can also substitute P. Understanding conditional logic is incredibly important for being able to do any kind of science or any kind of mathematics, because conditional logic allows us to do deduction. Without conditional logic, we're basically basing everything based upon the past, and we can't always necessarily understand whether or not the past is going to be true or not, if it's going to actually look like the future. In addition to that, if we don't observe something, we have no way of, in fact, determining whether or not something might be true without some kind of deduction or without conditional logic. And so conditionals, they really expand everything. All of mathematics is built off of conditional logic, because mathematics doesn't require us to actually have seen anything. All it requires us is to have objects that exist and logical connections between these, and these logical connections are with conditionals. So really, you want to go through, you want to study this, you want to make sure that you understand conditionals, because we're going to really be diving deeper and deeper and deeper into them. We're going to be using them throughout the entirety of discrete mathematics, and they're very, very, very important.